So now hopefully you got a sort of a feeling for laser diagnostics, for spectroscopy, the instrumentation. So now it's time for really going into the more applied areas, and I'll skip 2-3 lectures on the basic for laser-induced fluorescence, because I think since I only have 4 lectures, I will focus on the application. And that will be engines, gas turbines, furnace, bio applications. But before that, I just want to remind you a little bit on I showed something like it yesterday. What is laser-induced fluorescence about? Now you remember the energy levels that we discussed, the electronic ground state to excited state. And the basic idea for laser-induced fluorescence is that you tune your laser to the specific absorption band of the molecules you're interested in. And here, I mean, it's very well known in literature where the different molecules, atoms absorb. So for example, if we want to detect NO, we know that you have to have an absorption wavelength at around 226 nanometer. You know that the emission that will take place is between 250 and 300 nanometer. For OH, you know that this is at 280 nanometer, this is at 310 nanometer, and so on and so on. So all of these wavelengths are very well known. And the species specificity well, you see, English could be difficult. It's given by that you can, on one hand, hit directly on the absorption wavelengths, and you know which wavelength to look for. So you have 2 ways to separate that you really look for the right species. And that's why it might be a problem when you come to large molecules, because they have a lot of bands, and as I said, it's not necessarily the case that you can distinguish them neither through the excitation wavelength nor through the emission. So for example, the polyaromatic hydrocarbons that I described, they look pretty much the same. So the smaller the number of atoms in the molecule, the better. So that's why most of the work that has been done is on molecules of 2 atoms, of course, but also on diatomic molecule, 3 atomic, and some higher. And as I described yesterday, this gives a high sensitivity. You can go down to ppm, maybe ppb levels. You can do 2D imaging. I will repeat that. It's a spontaneous technique, which means that you might have to fight the background radiation. Just imagine if you want to measure in a welding torch. A welding torch is very intense. And that's why you have to gate your detector. Otherwise, you will saturate the detector with the background emission. So you gate your detector, and then you are species specific on the excitation and emission wavelengths. You can measure temperature and concentration. Actually, you can also, in principle, measure velocities by looking at the line shape, which is Doppler broaden. So that could be done, and we have done that in the past, but it seems like you have to go to very high velocities in order to do velocity measurements. But this is, of course, interesting because I think that one of our greatest challenges in the diagnostic community is to come up with a complement to PIV and LDV where you don't need to seed particles. You would like to look at the molecular species. And then, as I said, we have looked into in others the possibility to look at the Doppler shift. But that seems to be restricted to on the order of 50 meters per second. So that's not for low velocity experiments. But for high speed velocities, you can do that pretty easily. And then another thing which I might comment on today, which I didn't bring up yesterday, is the quantification problem. In laser-induced fluorescence, you're interested in the ground state population, right? I mean, in order to feed into models, this is the number density you need. But when we look, we really are detecting from the excited state, and since not all of the excited species give rise to photons, we have a problem. Maybe 1 out of 1,000 emit radiation. The other is lost through collisions. And you don't know how much they lose with what colliding partners, at what temperature, what pressure. So that's why still I would say that most laser-induced fluorescence images that are shown worldwide is nice pictures, not necessarily quantified in terms of ppm. So this, I think, is also a thing that we have to work on, and I don't have time to go into how that could be done, but there are various ways how you can convert this emission light into number densities, but it's not trivial. Okay, and also repetition from yesterday, I think this is very important. You'll see a lot of images, and we do that by planar laser-induced fluorescence, meaning that we have a laser beam like this, and then we use one of these special lenses that I mentioned that is only focusing so that you have the laser beam like this. You keep the height, but you focus in one direction, so you create a sheet. So this sheet goes through the flame. You change the color of the laser beam to exactly match the species you are interested in. Then you image that with a lens onto your two-dimensional image intensified detector, and then you can get in one laser shot the distribution of the species you're interested in. So that's sort of the basic idea for two-dimensional measurements. So with that, when we go from a laminar or turbulent laboratory flame, we have, and out in the real world, we have special challenges. We have to go to high pressure. High pressure is a complication because that means that the number of collision increases. That means that the loss that we have in laser-induced fluorescence is increasing, and very few detailed experiments have been done to quantify this. You also have a pressure broadening of your line width. So that means that most of the work that have been done in our lab and in others, in, for example, engines, is still pretty qualitative. We get an image, and that could tell us something. But really, in order to understand what is going on, more work has to be done at high pressure under laminar condition. And that's why we have set up a high-pressure laminar flame, on one hand to study high-pressure combustion, but maybe more importantly to try to understand how would a spectra look like if you go up to 20-30 bar. Do we understand the interaction between the laser and the molecules? Could we quantify it? So this is, I would say, very important for the future. Not too much has been done there. We might run into problems with limited optical access. If we want to do experiments in a big fire experiments in a boiler, engines, gas turbines, we have to have optical access. We have to put a window into this device. And that might not be too easy always. We many times have a sooty environment. If we want to study soot, of course, I mean, then it's straightforward. But if we want to measure concentration NO in a sooty environment, and then we might want to do experiments with high sensitivity, we want to increase the laser power, then we might run into problem with the breakdown, as I mentioned before, because the number of particles decreases the threshold for breakdown. And if we have a breakdown, meaning that we get a spark, then the detection measurements is ruined. So that's the upper limit. that means that we can't use all power that we have. And in a sooty flame, that is a problem. If we measure in a sooty environment, and if we want to look for soot, then of course it's good to have laser-induced incandescence. Laser-induced incandescence is a technique to measure on soot particles where you, by purpose, heat the particle with the laser beam, and then you look at the increased Planck radiation. That's of course very important when you study soot. But if you want to study other species, then of course the laser-induced incandescence will be a background. And that background will be on a time scale where our fluorescence is. So we can't gate it. And then we have a problem. If we have a lot of particles, we have Mie scattering from particles, which give rise to a huge signal. And even though we might have good gated detectors, we have filters, this might kill the signal if we have a lot of particles. And then if we have practical fuel, with practical fuels I mean diesel, gasoline, kerosene, then we'll also might have problems. We have, for example, if we want to do experiments in the UV, these fuels, a lot of them, absorb heavily. That means that the laser beam might not go through. It just be absorbed. Or if we go in, I have it here. If I have just say that it's a flame, it could be an engine or whatever. This is my laser beam going like this. So the first is extinction. That means that if we come in with 100%, if we end up with 1% after the engine or the flame, then of course we have a problem because the laser beam is attenuated. Not by scattering, not by particles, but just by the absorption of the fuel itself, which is the case in the UV. It's heavily absorbing. And not only that, you remember that we image with a lens onto a detector, right? And that means that here, on the way from the engine or flame to the detector, the emission might be absorbed. And that is what is called trapping. So that's another practical problem, that you'll have both extinction and you'll have trapping. And you might also have background fluorescence. If I illuminate kerosene or diesel, I mean, it gives a huge signal, fluorescent signal. And of course, that signal can swamp my signal, my real signal. And then we talked about the intrusiveness. If you have this kind of big fuel molecules, if you have too strong laser, you might photodissociate the fuel molecule, and you might give rise to C2 emission. C2, I mean, what's the blue emission that you saw from the flame? But here we can photolyze the fuel molecules to create C2 radicals. So these are sort of problems. And of course, if you have windows, you know, if we have, as we have to have, for example, in a diesel engine, and if the fuel is getting onto the windows or soot, then we have a problem. And in some cases, it might not take more than maybe a minute or so, and then the window is totally black, and the laser beam won't go through a black window. So all of these are practical problems that is very hard to foresee when we are asked to do some practical measurements. Where will be the main problem? Very often, I would say that we can can solve the problem, but it's hard to say that will be the problem, because it depends on the fuel, it depends on the optical excess, it depends on the number of species of the species we want to measure we have. So if we take some general applications, for example, engines or gas turbines, if we want to visualize the fuel, that has been of main interest from the engine gas turbine manufacturer. They want to see, for example, in a direct injection engine, where is the fuel? And then we have, I would say, two alternatives. Either we can use the real fuel, the gasoline, the diesel, whatever. And then we have some positive things about that. That's of course what the engine or gas turbine manufacturer wants. They want to have their real fuel, their fuel. And generally we have very strong signal. As I said, diesel, gasoline, it gives a huge signal. We'll never have problem with the signal. Then on the backside, what are we really detecting? We are sending in a laser beam at a certain wavelength. We get a lot of fluorescence. But what is really giving rise to the fluorescence? If we hit kerosene or diesel or gasoline, it consists of hundreds, maybe thousands of individual hydrocarbons. And we have no idea what gives rise to the fluorescence. So how can we from our experiments compare with experiments? We use for example, if we go to Volvo, they use some kind of gasoline. How could we compare that with colleagues in China or in the US or wherever? They have different fuel. Is it the same species that give rise to fluorescence? Do we draw the same conclusion? How are we influenced if we don't know what is giving rise to the fluorescence? What is the influence from temperature? What is the influence from pressure? What is the influence from quenching, the loss mechanism of colliding partners? We have no idea. So that's I would say a main problem. There are a lot of several nice features, but we have this problem. Then we have the other alternative, that is to use one or two component fuel where we add a specific tracer. For example, isooctane is a one component fuel. It does not give rise to any fluorescence. And then we can add small amount of another species where we can control exactly. And then we know what is giving rise to fluorescence. And the nice thing with this is that then we know we can measure, estimate the fluorescence characteristics. We can quantify the air-fuel ratio. We just don't get nice images. We can quantify this to get in a special point what is the actual air-fuel ratio. And then, of course, on the backside is that the engine manufacturer might not want to use this kind of idealistic fuel. So here we have two choices. And I'm not saying which is the best choice. We have chosen this one. When we work together with our car manufacturing companies and truck in Sweden, Scania and Volvo. On the other hand, I know that others, for example, General Motors, they have used this one. So it depends what really you want to have from your experiments. So I say we have not really done too much of this. But one exception, and that is when we did experiments together with Volvo Air Corporation. in the big fighter, which I described yesterday, they were not willing to use anything but kerosene. So the images I showed yesterday was just fluorescence from kerosene. I don't have any idea what gave rise to this. But in their case, I mean, there were no alternative. So the company decided, you have to go for this. And still, I mean, you could see in the image I showed yesterday that when you increase the power of the afterburner, you started to detect the fluorescence. It's very qualitative. But sometimes, I mean, you have to go for this, sometimes you have to go for this. But when you go for this, which we have done, then we put a lot of effort trying to understand how, if we have a fuel like isooctane, and then we add 3-pentanone, then what we are detecting is not isooctane, it's 3-pentanone. And then we have to understand or believe that this is following, the 3-pentanone is following the isooctane. We have to look for that they have similar vapor characteristics. The tracer have to have a high signal strength. We have to minimize the influence on the combustion so that we don't change the tendency for knock or something else. We'll have to have a low absorption of the exciting laser beam for the reason I mentioned there. It should be linear in dependence on concentration and laser intensity. We should understand the emission and absorption characteristics. We want to have a weak dependence on pressure and temperature, or no sort of strange quenching from oxygen. So before applying this in the engine, as I will describe later, we spend a lot of time, and more or less a whole PhD, just trying to understand the spectroscopy, the physics of 3-pentanone as being a tracer in engine experiments. Just to show you, here is diesel. We excite at 266 nanometer, and here we got the fluorescence. I have no idea what this is. I mean, this is just the fluorescence from the diesel we happen to have. If you have diesel here or in China or whatever, this might look different. But it's a huge signal. I mean, you see it with the naked eye. It's tremendous, and it's very nice in that sense. Here we have the 3-pentanone. This 3-pentanone looked the same in Lund, Iran, US, wherever. I mean, we know exactly how this spectra look like. So this is the advantage with that. Okay, so now if I go a little bit more into how to use LIF, and first in an engine, and I don't know how much into engines you are, but I mean this, and here we collaborate with the engine division. We are not expert in engines. So here we work very close with the division of combustion engines, and they actually build engine with optical excess. So they put, in this case, a liner of quartz where our laser beams go, and then we have a piston with transparent heading, and so the laser beam comes in like this. We detect through the piston onto a mirror, and here is the camera. So this is a lot of engineering to get this going, where we really haven't participated at all. And I think that's very nice when we can keep to what we are supposed to be good at, doing the measurements. The engine division are good at this. And then they just prepare the engine. We came with our lasers. We do the experiments together. That has been the idea for 30 years almost. So here is, if we look with the camera up through the piston, you can see the the inlet and exhaust valves, and you see the spark plug in the middle. And then the laser beam comes like this, so the images we detect goes like this. So these are the first measurements we did many years ago, and this was in a European project, and the aim was to develop this and try to see how the air-fuel inhomogeneity influenced the cycle-to-cycle variation. So in that case, of course, we have to come up with a technique that worked, and we find out this 3-pentanone seeded in isooctane. And in this case, after all of this fundamental work, here is the sort of the was, by the way, a slightly different setup than what I described previously. This was with the windows in 90 degrees. But here are sort of different individual measurements. Here you can see the spark plug. And here, the nice thing with this is that here it could be estimated, the air-fuel ratio. So here in each individual point, we can decide what is the air-fuel ratio in the spark plug at the time of ignition. And then you can see here it's richer, and here it's weaker, and then a lot of images like this could be used to compare to the cyclic variation later on. Then another experiment was done, and in this case we didn't have an optical excess easily, but instead we had the laser going through. This was in a direct injection spark ignition engine. So here we used a more or less standard endoscope that was introduced into the spark plug to see how the fuel was distributed. And this was in a direct injection engine, so we could see that the fuel comes in here, hit the piston, directed towards where the spark plug is, and here is the laser sheet. So the aim with this was to compare with CFD. Here is a CFD made at Volvo, and this is at the laser-induced fluorescence. It should run. Yeah. So this is at different times, not recorded at the same cycle, but you could see that a qualitative agreement, and as far as I understood, this helped the modelers at Volvo to improve their models how the fuel was vaporized. Don't ask me the detail, but we provided this, and then out from this they could sort of improve their model for vaporization. Then we have also done a lot of work on simultaneous measurements of formaldehyde and OH. And formaldehyde especially formed in low temperature region in HECI engines, and Lund has had a great interest in HECI engines. So we started to look into how could we measure formaldehyde, and then we looked into the spectroscopy, the background, and that's, as I said before, we have to understand how the spectroscopy looks like, where to excite, how does the emission look like, what kind of optical filter do we need. So this is when we use an excitation wavelength at 355 nanometers, then we see that the spectra look like this. That is sort of the base for trying to understand as well as possible how the technique would work in an engine. And then this is the experimental setup. So here we have one laser producing 355 nanometers, one laser, YAG laser, pumping a tunable laser together with the additional optics where we produce the wavelength where OH absorb. So that means that we have two laser beams, and then we use this dichroic mirror that I described. It reflects the 355, transmit the 280, go through a lot of optics, filters, lenses, go through this optical engine, detect, and now we have two detectors, two simultaneously gated detectors corresponding to the fluorescence from the formaldehyde. And if you look back, I mean, here we have a filter which is in the blue-green region, whereas the OH is in the ultraviolet region. So they don't overlap. So we don't have any problem with interference from them. And then we have two gateable detectors. And then we can get images like this. So these are images not recorded during one cycle. It's different cycles, but still you could see, and this is in a direct injection HCCI engine. This is the injection of the fuel, and then you could see that early in the combustion, in the low temperature regime, you produce formaldehyde with this color, and then later in the cycle, this sort of the real hot flame starts to ignite, and here you have more or less only OH. So although, I mean, these are not quantitative, it's qualitative image, but still it gives the engine people and the engine industry quite a good overview how this engine works and how to develop this kind of engine in an optimum way. And then I described before the high-speed system that we built in the early 2000s, where we had sort of 4 individual double-pulsed system, and then we, with various filters and optics, I don't have time to go into detail, but essentially an ordinary YAG laser work on 10 Hertz. So you get one pulse, then 100 milliseconds later you get another pulse, and so on. But in this case, for each occasion, you have 8 pulses, where you can vary the time between them. And then we have this very high-speed camera, the framing camera, that also have the possibility to capture 8 images. So if you combine this and that, then we have a laser-induced fluorescence system able to make a movie during one cycle of this phenomenon. And this is one of the first can run the movie. It's not a long movie, it's an 8-image movie, and here you can see the 8 images. This is in a spark-ignited engine where we use isooctane and 6% of 3-pentanone. So what you see here is the before ignition. Essentially, you have a homogeneous, more or less, distribution of the fuel. So the white here is the fuel. And then the ignition starts. So the lack of signal, the black is lack of signal. So then you can see how the fuel is consumed during one single cycle. And you can see that this is pretty stochastic, but it's a flame development, clearly shown in this case. And then it can come, well, not in this, but this is another where we looked in this direct injection spark ignited engine, where you can see how the fuel is directed up to the yeah, it's pretty fast. So the aim is, how would the injection of fuel be made in such a way that we get an optimum air-fuel ratio close to here is the spark plug. So it's guided through the piston, so that the fuel comes in, hit the piston, and is directed through this up to where you have the spark plug. And this is also showing OH. Instead of showing as I showed in the previous, it was a lack of signal when it was ignited. Then this is sort of the other way around. Here we are looking at the flame itself, showing essentially the same thing, but now we see actually how the flame, it starts, it develops, and you can see that it's a sort of a flame development. Yeah, I didn't have that. I thought that, but we have done the same in the HECI, and the HECI is a completely different combustion mode, where you have a sort of a auto ignition more or less all over the place. It's a completely different way of flame. It's not a flame development, but how the fuel is consumed as compared to the spark ignition engine. Then I haven't gone into detail previously, but I mean, it's also possible to measure temperature. If you choose two specific wavelengths in the molecular atom of interest, you can probe the Boltzmann distribution. And that's what we have done here in this engine. We produce two specific wavelengths. They are overlapped, sent into the engine, and then we have two detectors, and then we compare them on a pixel-to-pixel variation, and could get how this is what the detector will see without any combustion going on. And here we can see that how the flame is ignited, and now it's in temperature instead, as a function of different crank angle degree. And there we just take advantage of how the population is on the different rotational vibrational levels. So what might have seemed very, very academic before the break is now actually converted into a real temperature. So that was on engines. Then we have done also a lot of work on gas turbines, since we are working very closely with Siemens. Siemens has a big plant in Sweden. And the first approach, and that was actually 20 years ago, when Siemens was called ABB Stahl, but it's the same company. But it was interesting because when we visited them in the late 90s, they had developed what is called a double cone burner. It's sort of a burner like this to increase the degree of mixing. And when we visited them, they wanted to see, would it be possible to see how well are fuel and air mixed? And they did that by seeding a little bit of CO, and then they measure with a probe at different location, which is of course tedious. And then we thought that this might be easy with the use of laser-induced fluorescence. So in this case, a small amount of acetone was seeded to the fuel. And then we looked at the acetone fluorescence. And here is the setup. We have a YAG laser. We produce 266 nanometer. And this is gone through a cylindrical lens so that we'll get a sheet, and the idea was to send this sheet just outside. This is the end of the cone. So we just outside we send this laser beam 2-3 decimeters, and then so the laser beam is coming here. Here we have the double cone, and then we have the detector and the camera looking straight into this. So we're looking right into, it was not burning, but we're looking right into the exhaust of this. And then we could see how well was the air-fuel mixed. Well, that was the aim. And here we could see, these are the images looking straight into the cone. And you could see that I don't think that this is pretty homogeneous at all. These are just different snapshots taken. If you average this, if you put them together, maybe you will get something that is pretty homogeneous. But they wanted to use this in order to see how much, for example, anode do they form. And then, of course, you have to look, how does the distribution look like on a time scale on the time of the production of this species. And what was interesting was that this could run live. We could see this live on the screen, so that the technician could change whatever knobs on this burner to get this homogeneous. So directly you could get feedback how well the air and fuel were mixed. So I think this is a nice way of how to use this in a practical way. I mean, you could directly convert these images, although, I mean, we couldn't say maybe that you have an air-fuel ratio of whatever, 0.3 or 0.5 or 1.5, but from these images, you could just directly change the knobs, and then you could get something which is homogeneous. Another approach related to gas turbines is together with Volvo Air Corporation in Trollhättan. They had 4 different burners where the burners had a swirl in different counterflow directions. And if you looked from this side, this looks like that. It's just impossible to see how are these flames interacting. So we were asked to make an experiment to have the laser sheet right in the middle and to try to visualize the flow interaction while running these very highly turbulent flames. So this was done on site. So this is the system, YAG system, the dye system that was constructed and set up in Lund, and then it was on a truck 350 kilometers up to Trollhättan. And here you can see the 4 burners, and here you also see the laser beam is coming in this direction, and then you detect with this mirror onto the image intensified CCD here. And we got a lot of images, surprising results, even for the modelers at Volvo Air Corporation. These are just some examples. They want to investigate various preheat temperatures, varying mass flows, varying equivalent ratio at various positions. So I just wanted to show, and this is not noise. This is OH emission from the flame. So we are in a mode of combustion, which is, I'm not quite sure where in the Borg diagram we are, but the engineers and the scientists at Volvo Air Corporation were extremely interested how this flame behaved in this very, very highly swirling flow. These are single shots, and then we of course made averages. These are also experiments. I showed these yesterday, but I could just describe again that this is the engine for the fighter that Sweden is producing, Saab. So it's very interesting to try to do experiments in this environment. And there, of course, came a lot of these practical problems, really to be close to this. I mean, we have to investigate how to put optics, how to put mirrors, how to put detectors in this room was a challenge because of the vibrations. We have to discuss with the people from the acoustic division in Lund how to produce. The mirrors are with holders, and when they were standing there, they were just vibrating all over the place. So it has to be put in a device which could stand the vibrations, because this building, the whole building was shaking, and you could see the exhaust miles away. So this is a monster to do experiments in. But I thought that this was a nice way to try to see would it at all be possible. And that's I think what is interesting. We had no idea whether this would work. Would it be possible to penetrate? Would you have beam steering? What would happen with the laser beam when you enter this very hostile environment? And that's what I mean, that it's very hard to say it works or it doesn't work. You just have to try it. And in this case, it worked out very nice, and I showed this yesterday, where they changed the degree of the afterburner, and you could see the emission from kerosene. So I can't quantify how much kerosene, but at least you could say that after 60% of the afterburner, you don't see any unburnt fuel. And then when it goes back again, it comes back around 60 something percent, 70, yeah. So that they were very happy to see that they could get this results. Okay, so now a little bit on furnace biomass environment. I don't know how it is here in Iran, but in Sweden and Scandinavia, it's a big pressure on how to use biomass, and especially wood particles, straw dust and things like that. So we have investigated a little bit also on pyrolysis and gasification. So here are some small pieces of wood where we heated that in an oven to see at different time scales what would come out. I mean, we just put this small piece of wood and then we shine the laser above the particle, and then you could see how we got emission at different places. And when we tried to analyze this, it turned out that part of this was actually formaldehyde that came out. So far it's more of demonstrations, but these are I would say very important to try to develop how to burn, gasify and burn particles. Then we have also more recently looked into if we put a small piece of wood, we want to measure the temperature above the burning particles. And we have used a similar technique as was used in the engine. So we can, here is the burner without the wood particle. Here we introduce the particle and you can see that it starts to burn. And these are at different times. We introduce this as time 0. And then we can measure above at different stages when this was burnt, and you can see how the temperature goes down above this. And this is also something that is very important to understand. And so far, I mean, at least I'm not an expert in biomass combustion, but we work with people that try to model this. And then, of course, they need reliable data. And that's exactly where we are now, trying to provide them with as much data as possible in terms of not only the temperature, but we have also made measurements on the emission of, for example, HCN, where we measure with pretty advanced technique. So we can measure above the furnace, above the particle, when the HCN was emitted. Then we also, some years ago, together with Sydkraft and E.ON, they were interested to see could we get a burner working with wood particles, something similar to sawdust. So this was built. It took some time to get this burner to work. And then we have windows, which we could use for diagnostics. And here we have, when we used fuel as propane as fuel, we could measure OH. In the highly particle-laden environment, when we did the same, we got something that looks like this. I have no idea what this is, but this just shows that here we probably have a lot of polyaromatic hydrocarbon, a lot of particles giving rise to emission. So of course this is a challenge, but at least we got a signal. Now we haven't continued this explicit work, but it shows that